Hello friends, welcome back to All About Structural Analysis and Design. So this video will give a complete insight of the design of dog-legged staircase. Due to the number of requests from the subscribers, I have taken up this particular problem which will show you the detailed design of dog-legged staircase. If you have gone through my RCC playlist, most of the elements have already been analyzed and designed. So this is the extension of my RCC videos. So this particular video will be helpful for the students as well as the practicing engineers. So this particular problem will be a design of dog-legged staircase. So here the data given is we have to design a dog-legged stair for a building in which the vertical distance between the floors is 3.6 meters and the hall measures, hall is nothing but the staircase hall, okay, so it is 2.5 meters into 5 meters. The live load is given as 3 kilonewton per meter square and the materials which we are using is M20 grade of concrete and Fe415 materials. So let's begin with this video. So first write down the given data. So as a usual practice in the design problems, first it is very essential to write down the given data. So what they have given is the distance between the floors is 3.6 meters. So distance between floors is equals to 3.6 meters. Then staircase hall is equals to 2.5 meters into 5 meters, okay, so this is also given. Then live load is given, so we will denote it as WL, that is 3 kilonewton per meter square. Then FCK is given as 20 Newton per mm square and Fy 415 Newton per mm square. So this is the small data they have given, and from this data we have to proceed with the further calculations. So first what we will do is we shall assume the dimensions of rise and tread, okay, so that is very important. Rise and tread, I hope everybody knows from the concept of building construction and drawing, okay, so rise and tread we have to assume. So for normal residential building, the assumption of rise is 150 mm and tread is 250 mm. So therefore now let us keep rise is equals to 150 mm and tread is equals to 250 mm. Okay, so this depends upon the engineers, okay, who are designing this particular staircase, and also with the requirements of the client you can fix up the rise and tread, okay. So now width of flight also can be assumed, also width of flight is equals to 1.2 meter. So already we have 2.5 meters with us. So each flight, okay, so dog-legged staircase means usually we will be going for 2 flights, okay. So the first flight is having a width of 1.2 meters and one more will be having 1.2 meters, okay. So therefore now height of each flight we have to find out. Height of each flight is equals to vertical distance of floors divided by 2. So what they have mentioned, the vertical distance between the floors is 3.6 meters, okay. So this is nothing but vertical distance that we have to divide by 2 because we want 2 flight dog-legged staircase. So 3.6 divided by 2, we will be getting height of each flight. So this is equals to 3.6 divided by 2, therefore 1.8 meter. So therefore the 1.8 meter will be the height of each flight. So this is the calculation you have to perform and you have to go with the next steps, okay. Now once you have fixed the height of each flight, that is 1.8 meters in this case, then you have to calculate how much risers are required for that particular flight, okay. So therefore number of risers is equals to 1800, that is nothing but height of one flight, okay, divide by 150, because the dimension of the riser we had assumed 150 mm. So when you calculate this, it will come as 12. So in bracket I'll write down in each flight. Okay, so 12 number of risers will be available in your each flight. Now once you find out the number of risers, the next step is to find out number of treads. So therefore number of treads, which is very simple to calculate, okay, is equals to number of risers minus 1. So that will become 12 minus 1, which is equals to 11. So in your each flight there will be a 12 number of risers and 11 number of treads. So like this way you have to calculate the number of risers and number of treads. So now you can easily calculate space occupied by treads. Space occupied by treads is equals to, that is 11 number of treads into 250, because we had assumed the size of tread as 250 mm. So this will come out to be 2750 mm. So this is the space occupied by treads. Okay, so now let us keep width of landing, that we can assume. Okay, this landing width we can assume. So now let us keep width of landing is equals to 1250 mm. So now once you have fixed up the width of landing, then we can easily calculate the space left for passage. Okay, therefore space left for passage. Okay, so the total the staircase hall was measuring 2.5 meters into 5 meters. So from that 5 meters, okay, that is 5000 mm. So we shall remove this space occupied by treads, that is 2750, and space of landing 1250. So once you deduct this, you will get 1000 mm space for the passage. So I will just show you the figure how it looks. Okay, so the textbook problem I have taken directly. Okay, so this is your staircase hall, so 2.5 meters into 5 meters. So in that the passage width we just got 1 meter, so this is the 1 meter. This is 2.75 meters space occupied by treads. So these are the treads. Okay, then we have assumed 1.25 meters, that is 1250 mm as the space for landing, and width of each stair we had taken 1.2 meter, 1.2 meter. Space 0.1 meter which remains is the this space which is left for the railing purpose and all. So this is the general arrangement of your stair hall. Okay, so now the basic arrangement has been done. So next we can calculate the loads and other things. Then the next step will be calculation of effective span. Okay, the landing slab, I'll write down here some wordings. Okay, the landing slab is assumed. So this is, you can write down in your answer sheets also. The landing slab is assumed to span in the same direction as the stair. Okay, as the stair means the flight. Okay, and is considered to act together, and is considered to act together, giving rise to single slab. Okay, if you have seen the practical aspect while casting the staircase, so we don't cast a landing slab as different, and then the height of each flight or different types of flights at different time. So what we assume is the landing slab which we are going to provide is assumed to span in the same direction as the stair. Okay, because it acts together. Okay, so giving rise to a single slab. So therefore now assuming bearing which the slab will rest, okay, as 230 mm. So based on this we will calculate the effective span. Therefore L is equals to, the space required for tread was 2750, then landing slab is 1250, and the bearing which we had assumed is 230, that is divided by 2. So L comes out to be 4115 mm or 4.115 meter. Okay, so once you calculate the effective length, then the calculation of loads and bending moment we have to start. So therefore the next step will be calculation of loads and bending moment. Okay, so now you have to assume a thickness of waste slab. How much to assume? That is given by the thumb rule, that is 40 mm to 50 mm per meter span. Okay, so this is the thumb rule you have to follow to assume thickness of waste slab. Okay, so I'll write down here. Now assume thickness of waste slab as 40 mm to 50 mm per meter span. Okay, so this is very important while calculating the loads. But otherwise, because if you don't assume the thickness of waste slab, you cannot calculate the loads, and in turn it is very difficult to find out the bending moment. So thumb rule says you have to assume between 40 to 50 mm per meter span. Okay, so now in this case we will assume as 50 mm. Okay, so therefore thickness we will assume as 50 mm into 4 meters. That comes out to be 200 mm. So which is quite a good thickness for the waste slab. So therefore now we can calculate dead weight of waste slab. So therefore dead load waste slab, that is W1 we will consider. Okay, so the W1 is given by, so now you have to remember the formula. T is equals to square root of R square plus T square, that is divided by T into 25. So this 25 is nothing but unit weight of the concrete which is being used in the reinforced cement concrete. Okay, so therefore W1 is, this T is nothing but thickness of waste slab, that is 0.2. Okay, so this, sorry, this is not is equals to, so this is multiplication. Okay, so 0.2 into riser we had taken as 150 mm, so it will become 0.15 square, plus trader is 250 mm, that is 0.25 square, divided by tread 0.25 into 25 kilonewton per meter cube is the unit weight of the concrete. So once you work out with this, you will get W1 as 5.83 kilonewton per meter square. So this is the dead load of waste slab. Now once you calculate the dead load of waste slab, then you have to calculate dead load of the steps. Now dead load of steps, we will denote it as W2. W1 was dead load of waste slab, W2 is dead load of steps. So that is given by R by 2 into 25. 25 is nothing but unit weight of concrete. So R is 0.15, correct, divided by 2 into 25. So once you work out with this, so W2 you will get 1.875 kilonewton per meter square. So this is how you have to calculate dead load of waste slab. So now you can find out the total load. Therefore total load W is equals to W1 plus W2 plus live load plus floor finish. Okay, so you will be providing the tiles on the floors, that also you may consider. So if you consider it is well and good, otherwise you can skip it, no problem. Okay, so W1 you have got 5.83, W2 you have got 1.875, live load was 3.25 will consider. Okay, so floor finish we will assume it as 0.25. So if you add all this, you will get 10.25 0.955 kilonewton per meter square. So this is the total load coming onto that particular staircase, not staircase, that each flight. Okay, so now you have to do ultimate load. WU, which is nothing but W into 1.5, 10.955 into 1.5. So W you will get 16.43 kilonewton per meter square. So therefore now the next step is to calculate the moment. So therefore mu is equals to WU L square by 8. WU you calculated, that is 16.43 just now. Effective span is 4.115 square divided by 8, and you will get this, the moment as 34.77 kilonewton meter. So this is your ultimate moment. So now we will check the D, whatever we have provided. D is nothing but thickness of waste slab, is sufficient to take this particular moment or no. Now the check for waste slab. Now check for depth of waste slab. Okay, so that can be calculated by mu is equals to 0.138 FCK BD square. So now this formula is applicable only when you are using Fe415 steel. Okay, so Fe500 and Fe250 if you use, so slight changes it will happen. Okay, so that you can work out, or you might have already worked out in your previous problems. Okay, so therefore D is equals to square root of mu divided by 0.138 FCK B. So here mu is 34.77 into 10 raised to 6 divided by 0.138 FCK is 20. So B will be taking as 1000 because we are designing it as a waste slab, and slab always the width will be per meter width. So 1000 mm width you have to consider. So once you work out this, so D comes out to be 112 mm, and the D provided is our 200 mm. Okay, so that 200 mm is inclusive of cover. Okay, so therefore D provided is equals to 200 mm, which is nothing but T, that is equals to thickness of waste slab. Therefore D dash we will assume as 20 mm. So therefore D will be 180 mm. Okay, 200 minus 20. So therefore D required is equals to 112 mm, which is less than 180 mm. Therefore the depth whatever we have provided is sufficient to carry the moment of 34.77 kilonewton meter. So once you have checked for the D, then you can go for the reinforcement calculation. Calculation of reinforcement. Okay, as usual again AST formula, that is 0.5 FCK by Fy 1 minus root of 1 minus 4.6 mu by FCK BD square into BD. So if you substitute all the things, that is 0.5 into 20 divided by 415, 1 minus root of 4.6, mu is 34.77 into 10 raised to 6, because in Newton millimeter we will substitute because all the things are in Newton millimeters. Okay, so FCK is 20, B again in 1000, that is 1 meter width, D is 180 square, because provided is larger than 112, and provided only we have to calculate for the calculation of AST, into B is 1000 again and into 180. So if you work out this, your AST comes out to be 573.15 mm square. So unit again is very important for AST. So once you have calculated the AST, then number of bars, the spacing of bars you have to calculate by assuming the appropriate diameter. So now for this case we will assume 10 mm diameter. Now using 10 mm 5 bars, small AST, that is pi by 4 into 10 square will give you 78.5 mm square. Okay, so this is area of 1 bar. Okay, therefore spacing is equals to, so AST, small AST, that is 78.5 divided by 573.15 into 1000. Why 1000? Because we are spreading this particular spacing for the 1 meter width of the slab. So therefore, so the spacing comes out to be 136 mm. So therefore, provide 10 mm 5 at 120 mm center to center as main reinforcement. Okay, we will not provide 136 exactly. Okay, so we will reduce the spacing so that there should not be any problem while distributing the AST for that particular moment, which is 34.77. If you increase the spacing, what happens? That will contradict your the moment capacity for that particular waste slab. So always it is better to decrease the spacing. So the final reinforcement will be 10 mm 5 at 120 mm center to center as main reinforcement. Now you have to provide the distribution steel also, right? So therefore provide minimum steel as distribution steel. Okay, so and AST minimum, if you have gone through my slab videos, I always stress on the check of minimum AST, that is 0.12% of gross area. So AST minimum is equals to 0.12% of BD. So 0.12%, 1000 is your B, and total depth is 200, that is thickness of waste slab. So this comes out to be 240 mm square. Okay, so this is your minimum steel you have to provide, and that will be your distribution steel. So our main reinforcement was 573, that is greater than minimum steel, which is okay, because it is greater than minimum steel. So therefore now what we will do, we will not provide again same 10 mm 5 bars because the AST is small. So therefore we will go for 8 mm 5 bars. So therefore provide 8 mm 5 bars. So therefore again you have to calculate small AST, that is pi by 4 into 8 square. You can go with 10 also, there is no hard and fast rule like that, you have to select 8 only. Okay, so you can select as per your requirements. Okay, 50.26 mm square. So therefore you have to spacing calculate again. So small AST, that is 50.26 divided by the 240 into again 1000. So this comes out to be 209.41 mm. So therefore provide 8 mm 5 at, we will make it as 200. Okay, 200 mm center to center as distribution steel. Okay, so this is how you have to calculate the main reinforcement and distribution reinforcement. So now this is the reinforcement detailing of the dog-legged staircase which we have just designed. So this is your passage, right? This is your space occupied by treads. That passage is 1000 mm, that is 1 meter. Space occupied by treads is 2.75 meters, that is 2750 mm, and this is the landing space 1250 mm. So landing, then stair, then passage. Okay, so these are the 12 number of steps which I have shown here, and this is the bearing of 230 mm. So whatever the straight line you are seeing here is the main reinforcement, that is 10 mm 5 at 120 mm center to center I have shown here, and this whatever the dotted portion is there, that is distribution steel 8 mm 5 at 200 mm center to center. So this 200 mm which I have shown is the from this space till the outer edge of that particular waste slab. right? So this is your 200 thickness of waste slab. So this is the floor level, and this is your landing. So this is how you have to show the detailing of dogleg staircase. I hope you have followed this particular design of dogleg staircase. If you have liked this video, please like it, share it, and don't forget to subscribe all about structural analysis and design, and also press the bell icon for the latest notifications of my videos in civil and structural engineering. Thank you, friends.